Hello friends, welcome to the second session on electronics. So in the first session, we have discussed about the types of semiconductors and extrinsic, intrinsic semiconductors, P-type, N-type semiconductors. Hope you have gone through the first session, first video, electronics 1. If not, go through the first video, then watch this electronics 2 for complete clarity on the concepts that we're going to discuss. Okay, right. Please be ready with your pen and paper. In this session, we're going to discuss about the diodes, types of diodes, and what is a diode, how is it formed, all about diodes. So if you're ready with your pen and paper, here we go. So first we have to discuss about the PN junction diode. What is a PN junction diode? See, already we have discussed about the P-type semiconductor and N-type semiconductor in our previous session. That is under the title Electronics 1. A P-type semiconductor is an extrinsic semiconductor with excess of positive charge carriers. Majority charge carriers are holes in P-type semiconductor. Whereas in N-type semiconductor, we have negative charge carriers as the majority charge carriers. Those are electrons. Now, if a P-type material, P-type semiconductor is properly sandwiched with an N-type semiconductor, this combination is called a PN junction diode. See, it is a device with one junction here between P-type material and N-type material, and there are two terminals. Diode. What is di? Di meaning two. So it is a device with two terminals and one junction. Understood? Di meaning two. Word generally stands for valves. It is a device with two valves. That means two terminals and one junction. Okay. When a P-type material is properly sandwiched with an N-type material, P-type semiconductor and N-type semiconductor, then a PN junction is formed. This is called a diode. So PN junction diode looks like this. See, when P-type material and N-type material are joined together, joined to each other, near the junction, see, this is the junction, right? Near the junction, at this junction, positive charges on P-type and the negative charges on N side, these two will recombine and they form certain region, the shaded region, which is of no mobile charges. Or simply, this region is depleted from mobile charges. There are no mobile charges. The charges or ions in this region are immobile. To the left of it, this is P-type material, and on the right side you have N-type material. To the left of this depleted region, we have free holes. These holes can move. And to the right of this, there are electrons which can move. But near the junction, whatever electrons are there on this side and holes on the other side, they form in recombination, and due to this recombination, this region becomes depleted from mobile charge carriers. These charges are immobile. So that's why this region is called depleted region. So at the junction, electrons diffuse towards P region. Electrons, see, these are the electrons. They move towards the P region, and the holes towards N region. Holes on this side, on the left side, they move towards the N region, and they recombine with each other. Because of this recombination, a depleted region or depletion region is formed. This leads to the formation of a thin layer around the junction, which contains no mobile charges. There may be charges, but they are immobile. There are no mobile charges. That is called depletion. And that particular region is called the depletion region. So coming to this depletion region, to the left of the depletion region, we have positive potential, higher potential, positive charges are there. And to the right, there are negative charges. So it leads to negative potential. Across this depletion region, there is certain potential difference, right? So the potential difference which is set up across the depletion layer prevents further diffusion of electrons and holes. And this potential difference is called the barrier potential, denoted by VB, the barrier potential. Understood? Yes. So for every PN junction diode, there is certain barrier potential, the potential difference across the depletion region. Remember that point. And this is the circuit symbol for a PN junction diode. PN junction diode circuit symbol. In this, see, this arrowhead indicates the negative side, and this side it is positive, or P side and N side, like anode and cathode. Okay, right. So that is the circuit symbol for a PN junction diode. Now, coming to the ways how it can be connected in a circuit, that is called biasing. How battery is connected to the diode, or power supply is connected to the diode. There are two ways of biasing, forward bias and reverse bias. Let us see what is biasing. The process of applying suitable potential difference across the diode is called biasing. See, a battery is connected here across the PN junction diode. So external potential is applied here. Already we have discussed about the potential that is there within the diode, barrier potential. Now there is a source of EMF externally, a battery or a cell. This provides additional EMF. Now there can be two types of biasing, as I told you, forward bias and reverse bias. So what is a forward bias? See, the circuit shown here is a forward bias circuit. See, battery positive terminal is connected to the positive terminal of the battery. This portion is connected onto the positive side of the diode, and battery negative terminal is connected to the N side of the diode. Such a connection is called forward bias. If the positive terminal, if the positive terminal of the cell is connected to the P region and the negative terminal is connected to the N region, not only that, and the EMF of the cell is greater than the barrier potential. EMF of the cell must be greater than the barrier potential. Then diode is said to be in forward bias mode. Forward bias mode. See, circuit symbol is shown here. This is positive, negative. This positive terminal of the battery is connected on the P side, and negative terminal of the battery is connected on the N side of the diode. Then it is called a forward bias combination. The diode is said to be in forward bias. So what happens in forward bias? See, in forward bias, a continuous current flows through the junction, means the diode conducts in forward bias. This is because of the majority charge carriers. Okay. So in forward bias mode, there is a continuous current flow through the junction or through the diode, or simply diode conducts in forward bias mode. Understood? Right. Applied voltage is opposite to the built-in potential V0, barrier potential. Applied voltage is opposite to the barrier potential. In forward bias, this is very, very important point. See, in forward bias, width of the depletion layer decreases. What is depletion layer? See, near the junction, a depletion layer is formed, right? On either side of this junction, some region has become immobile from the charges. There are charges, but they are immobile. Okay. When it is connected in forward bias, the width of this depletion layer becomes less, like this. So only this much is the depletion layer in this case. So width of the depletion layer decreases in forward bias mode, allowing the charges to cross this barrier and move on to the other side and lead to the conduction. So that's why the diode conducts in forward biased mode. Coming to the graph, barrier potential graph. See, without the battery connected, the potential difference is shown like this. V naught is the potential. This is V naught, barrier potential. But when battery is connected, this is shifted to this position with applied voltage V. Now, effective height of this is V naught minus V. Effective height becomes V naught minus V. See, barrier height is decreased in this case, and effective barrier height is V naught minus V. Is that clear? From this figure, this is the barrier potential graph. Now, minority carriers injection takes place in forward bias mode. Diffusion current flows due to electrons as well as holes. That is the speciality of semiconductors. Unlike conductors, in conductors, conduction is only due to electrons. In insulators, there is no conduction at all. But in semiconductors, conduction happens because of both electrons as well as holes. But the current due to these two in forward bias mode is in the range of milliampere. The current is less and the current is in the order of milliampere. Few milliamperes current will be passing through the diode and the circuit. Now coming to the reverse biasing, reverse bias, the title itself indicates what it is. If the positive terminal of the battery is connected to N side of the diode and negative terminal of the cell is connected to the P side, positive side of the diode, then it is called reverse bias. See, that's what is shown here. Negative terminal of the battery is connected to P of the diode. Positive terminal of the battery is connected to N of the diode. Connected in reverse order, right? That's what is reverse biasing. So in this type of biasing, positive terminal of the cell is connected to the N region and negative terminal is connected to the P region. What happens as a result? The width of the depletion layer increases and it becomes very much difficult for the charges, either holes or electrons, to cross the barrier. So they cannot cross the barrier, hence there is no conduction in reverse bias mode. Okay. In this mode, no current will flow across the junction. No current will flow across the junction. But in forward bias mode, current flows through the junction, conducts, the diode conducts. But in reverse bias mode, diode does not conduct. Okay. So here is a student. Hi, Iris. Okay. So in reverse bias mode, there is no conduction taking place. There will be very small current due to minority charge carriers and the small current is negligibly small. Negligibly small. That's why we say practically there is no conduction in reverse bias mode. Okay. So in one mode it is conducting, that is in forward bias mode, diode is conducting, and in reverse bias mode, it's not going to conduct. That is called the unidirectional behavior. So a diode acts as a unidirectional device, conducting in forward bias mode and blocking the current in reverse bias mode. Do you know whose function it is? Do you know any component in your household which allows current to pass through in one mode and which does not allow current to pass through in another mode? Getting any idea? It's a switch. See, switch conducts in on mode and does not allow current to pass through in off mode. Even diode acts the same way. It allows current in forward bias mode and it does not allow current to pass through it in reverse bias mode, unidirectional behavior. Okay. So the direction of the applied voltage is same as that of the barrier potential in reverse bias mode. Width of the depletion layer increases in this case. Width of the depletion layer, for your better understanding, see across the junction there is a depletion layer. This is the original depletion layer, right? But when it is connected in reverse bias mode, the depletion layer extends up to here. This would be the depletion layer now. See what happened to the width? The width is increased. So width of the depletion layer increases in reverse bias mode and it decreases in forward bias mode. Remember that. And if there is any current passing, literally very small magnitude of current will be passing through that due to minority charge carriers. You can consider it as 0. But if you want to measure that current, that will be in the order of microampere. Very, very small current. Micro stands for 10 power minus 6. 10 power minus 6 ampere. Whereas in forward bias mode, it is in the order of milliampere, where milliampere is 10 power minus 3 ampere. So it is differing by 1000 times. Isn't it? So much smaller the current is in reverse bias mode. The diffusion current decreases enormously. That's why there is no conduction in reverse bias mode. The current under reverse bias is essentially independent up to the breakdown voltage, and this is called the reverse saturation current. Reverse saturation current. Coming to the barrier potential graph, see, with the battery connection and without battery connection. When battery is not connected, this is the height of the barrier potential V0. Okay, potential barrier across P and N regions. But when battery is connected, it rises up to this level with V over here. So barrier effective height becomes V0 plus V in reverse bias mode, whereas in forward bias mode it was V0 minus V. Okay, so barrier height is increasing in this case with effective height V0 plus V in reverse bias mode. Understood? Yes. Now coming to characteristic curve of junction diode, PN junction diode. These are called the VI characteristics. The graphical relation between voltage and the current. Graphical relation between voltage and the current in a forward bias and reverse bias diodes are given by the forward characteristics and reverse characteristics. And these are called the VI characteristics, voltage versus current characteristics. Okay. See, in this part stands for the forward bias, and the second part, this part stands for the reverse bias. Forward bias characteristics are shown here, V versus I, and the current is in milliampere range. And in reverse bias, the current is in microampere range, that is shown in this graph. Okay. So if you observe the forward bias characteristics, with increase in voltage, current gradually increases like this. Okay. And here Vt is called the threshold voltage. But when it comes to the reverse bias characteristics, with increase in voltage, there isn't much increase in the current. There isn't any appreciable increase in current up to certain value. But after a particular voltage, current increases abruptly. This particular voltage where current increases abruptly is called the breakdown voltage. Breakdown voltage, and also known as knee voltage, as it is in the shape of your knee. Okay. And here Vt is the threshold voltage and Vbr is the breakdown voltage. These are the forward and reverse bias characteristics, VI characteristics of a junction diode. Now, see, in forward bias mode, the current increases rapidly And in reverse bias mode, the current remains very small. It remains very small over a wide range of voltage. So in forward bias mode, current is increasing rapidly. With increase in voltage, current is also increasing and the current is in milliampere. But when it comes to reverse bias, though voltage is increased, there isn't much increase in current. But after this breakdown voltage, current increases very rapidly. Okay. So that voltage is called the breakdown voltage. If reverse bias is made high beyond VBR, breakdown voltage, the covalent bonds at the junction break down. Covalent bonds at the junction break down. What is a covalent bond? It is a bond formed by combination of two electrons, right? If two electrons are contributed by two atoms, it leads to formation of a covalent bond between those two atoms. If this bond breaks, we get more and more electrons, free electrons available. So it leads to abrupt increase in current. So the covalent bonds at the junction break down and reverse current increases abruptly to a very large value. This process is called avalanche breakdown. Okay, that is avalanche breakdown. And this avalanche breakdown is due to breaking of the covalent bonds near the junction. Next, the resistance offered by the diode to the flow of current is given by R is delta V by delta I. This is dynamic resistance. Dynamic resistance of the diode, which is resistance is nothing but the opposition to the flow of current, right? Here it is changing current. That's why delta V, delta I. So the dynamic resistance of the diode is the opposition offered by the diode to the changing current and is given by RD. D here represents the dynamic. RD is delta V by delta I. Now, coming to the applications of this junction diode, it can be used as a rectifier. Do you know a rectifier? Have you ever used it? Do you have any idea about the rectifier? Just think of it. Every day, whether you know it or not, you have been using it every single day. Rectifier is the device which converts alternating current into direct current. AC to DC converter is a rectifier. Simply, your mobile charger is a rectifier. Your laptop charger is a rectifier. The output is DC when input is AC. So the process of conversion of AC, alternating current, into a direct current is called rectification. And the device which has a circuit performing that action, and the device is called a rectifier. Device which consists of a circuit which convert an alternating current or even voltage, alternating voltage into a direct voltage or alternating current into a direct current, that is called a rectifier. Okay, what is a rectifier which converts AC into DC? For that matter, your mobile charger is a rectifier. Okay, now a PN junction easily conducts when it is connected in forward bias mode and practically does not conduct when it is in reverse bias mode. That is unidirectional behavior of a diode, right? So this property of the diode, the unidirectional conduction, is made use in constructing diode rectifiers. Diode rectifiers. Here we have two types of rectifiers. One is half wave rectifier. Half wave rectifier known as HWR in simple. Another one is full wave rectifier. Full wave rectifier, FWR. Okay, so two types of rectifiers we have. The first one is half wave rectifier. HWR stands for half wave rectifier. As the name indicates, it rectifies or it converts half of the AC input input signal into DC. A device which converts one half cycle of an AC into DC is called a half-wave rectifier, and the half-wave rectifier is shown here in the figure. Half-wave rectifier. Input is AC. You know, AC signal is like this with a varying positive and negative half cycles. That is AC input. Here is a transformer. This part is a transformer. Okay. Now, primary of the transformer is here, and this is the secondary of the transformer. After the secondary of the transformer, see, you can find a diode connected here. Diode. After that, you have a load resistance across which the output can be taken. Okay. Now, how does it work? See, when an AC signal is passed through this, first positive half cycle will be passing through this. For the positive half cycle, this is positive half cycle. Diode is in forward bias mode for the positive half cycle. So it conducts that half cycle. That's why, see, this positive half cycle of the input is carried forward. For the negative half cycle, like this, negative signal is given to the diode positive. That means it is in reverse bias mode. In reverse bias, we know diode does not conduct. So this negative half of the cycle is not passed through this diode. And next, another positive half cycle comes into picture. So that will pass through it. This negative part is missing. That's why you have a blank in this region. And again, positive half cycle that passes through the diode. And this negative half cycle is not passed. Understood? What is a half wave rectifier? Half of the wave gets rectified in this. Okay. Now coming to the parts of this circuit diagram, P stands for the primary of the transformer, S stands for the secondary of the transformer, D represents the PN junction diode. Okay. RL is the load resistance across which output DC voltage is taken. Voltage is always measured across the resistor. So load resistance, across this load resistance, output voltage is measured, and the output voltage looks like this, unidirectional. It's not varying between positive and negative half cycles. That's what is DC, direct current. Whereas input is AC, alternating current, alternating between positive half cycles and negative half cycles. Understood? Now, see, though the output is DC, there will be some component of AC present in the output. Overlapped on the output, we'll have AC components also. Those are called ripples. Ripples. So the output DC voltage of the rectifier has some AC components superimposed on it, and these are called ripples. The AC voltage variation in an output or amount of ripples compared to the DC voltage is expressed in terms of a ripple factor. A ripple factor. Then how to get rid of this AC component in the output? Output has to be DC perfectly, but there will be small components of AC. If you want to remove that AC, we need to connect a capacitor in the output circuit. Capacitor acts as AC filter. Capacitor acts as AC filter. So by connecting a capacitor in the output circuit, that AC component can be removed. Right. Now, what is this content of a ripple that is expressed as ripple factor given by RMS value of AC components in output voltage? RMS stands for root mean square value, RMS value of AC components in output divided by DC value of output voltage. And this value comes out to be 1.21 for half wave rectifier. Ripple factor is 1.21 for half wave rectifier. Okay. So half wave rectifier is very inefficient, not very efficient. This is very inefficient. Since useful power is obtained only for half of AC cycle, only half of the wave is getting rectified. The other half we are missing. So it is not that efficient. Anyway, whether it is perfectly efficient or inefficient, how to measure its efficiency? So the efficiency of a rectifier is given by output DC power by input AC power. To express it in percentage, multiply with 100. So output DC power by input AC power into 100 is the efficiency of a rectifier. For half wave rectifier, this value is 40.6%. The efficiency denoted by eta of a half wave rectifier is only 40.6%. Okay. Now, where do we find the applications of this half wave rectifier? Large application of half wave rectifier is found in amplitude modulated radio receivers to perform demodulation of the signal. Demodulation is separation of the message from the carrier wave. You might have learned it in the communication systems. So that for the demodulation purpose, these half wave rectifiers are used. Understood? Yes. Now, after half wave rectifier, here we have a full wave rectifier. The name itself indicates full wave rectifier. Both the half cycles of AC input are rectified in this full wave rectifier. The device which produces rectification of both halves of an AC input is called a full wave rectifier. So this can be achieved using two PN junction diodes and a transformer with a center tapping. This is the transformer shown here. The transformer with a center tapping. See, output is taken from the center of the transformer. That's what is called center tapping. Output is taken from here across the load resistance. And as in case of half wave rectifier, here also there will be some AC component present in the output. To get rid of that, a capacitor can be connected here. Capacitor acts as AC filter. So the capacitor filters the AC component, ripples. Now, see, when AC is fed to this transformer here, AC contains alternating positive and negative half cycles. For positive half cycle, one diode conducts. It will be in forward bias mode for one half cycle, positive half cycle. And for this positive half cycle, the second diode will be in reverse bias mode. So it does not conduct. Means the first positive half cycle passes through the first diode, let us say D1, the top one. When it comes to the negative half cycle, the second diode will be in forward bias mode, whereas first diode is in reverse bias mode. So first diode does not conduct, but that signal is passed through the second diode, D2. Anyway, that half cycle is also passed. So positive half cycle that comes here, and this negative half cycle is passed by the second diode as it acts as forward bias mode. So that is also passed. Okay, the negative half cycle. Again, positive half cycle comes over here, and this negative half cycle also comes into existence in output. Understood? That's how this full wave rectifier works. As usual, coming to the components P, S. P stands for the primary of the transformer, S is the secondary of the transformer, T is the central tapping of the secondary coil, RL is the load resistance. RL is the load resistance across which the output is taken. And to filter this AC component present in DC output, a capacitor will be connected in the output circuit. Then the circuit looks like this with the D1, D2 as PN junction diodes. See, here is the capacitor. Right? So due to this capacitor, the AC component can be removed. D1 and D2 are the two diodes which simultaneously act as forward bias modes, and they pass these two half signals, positive half and negative half of the AC input, and whatever AC component is present in the output finally, that can be filtered by this capacitor. Remember that point. Okay. Next. In full wave rectifier also there is some AC component present or ripples are present, and that ripple factor is given by RMS value of AC components in output voltage divided by DC value of the output. RMS value of AC by DC value of the output. For full wave rectifier, that value is 0.48. Do you remember what is this value for a half wave rectifier? See, for a half wave rectifier, it is 1.21. But for full wave rectifier, it is only 0.48, much less than a half wave rectifier. Hence, there are less ripples in full wave rectifier output compared to the half wave rectifier output. And coming to efficiency also, this full wave rectifier is much efficient than a half wave rectifier, and literally it is twice that of the half wave rectifier efficiency. The efficiency of a full wave rectifier is 81.2%, whereas for a half wave rectifier it was 40.6% only. This is for half wave rectifier, and this is for full wave rectifier for 81.2%. Double of 40.6 is 81.2. So full wave rectifier is more efficient than a half wave rectifier. Now coming to the current in output, DC current, it is given by 2 into I naught by pi, where I naught is the peak secondary current. In the transformer we have primary and secondary. So whatever is the current, peak value of the current in the secondary, that is I naught. Then output DC current is 2 times I naught by pi. Once if you know current, you can find voltage also, VDC, multiplying with load resistance. See, VDC is IDC multiplied by RL, load resistance. That is 2 I naught by pi into RL. Whereas I naught into RL is nothing but V naught, peak voltage. So 2 V naught by pi. 2 V naught by pi its values. And 2 by pi is 0.636. So this overall value is 0.636 V naught, where V naught is the peak value of full wave rectifier output waveform. Understood? Now, since a full wave rectifier requires a central tapping, a transformer used will be larger than a half wave rectifier transformer. In full wave rectifier, a bigger transformer is used. And also it contains a capacitor circuit to filter the AC component, both half wave rectifier and full wave rectifier. Now coming to other types of diodes, we have different varieties of diodes. One such is Zener diode. This Zener diode is operated in reverse bias mode. It is designed to operate under reverse bias in the breakdown region. Zener diode is operated in reverse bias mode and it acts as a voltage regulator. Zener diode is fabricated by heavily doping P and N sides of a junction. See, Zener diode, it is fabricated by heavily doping the P and N sides of a junction. P-type material and N-type material, these two are heavily doped in fabrication of the Zener diodes. Coming to the VI characteristics of a Zener diode, it looks like this. See, with increase in voltage, the current increases in forward bias mode, this part, and it is measured in milliampere with an ammeter in the range of milliampere. But Zener diode is particularly operated in this mode, reverse bias mode. See, though voltage is increased over a wide range, there isn't much increase in current. But after a particular value, current increases rapidly. Already we have discussed this point. Okay, so it acts as a voltage regulator. At G0 breakdown, a current suddenly increases to a high value and the voltage across the diode remains constant. Only current increases, but the voltage value is almost constant. That is the speciality of this G0 diode. Okay. See, the symbol of G0 diode looks like this. Usually, a diode is shown like this. This is the diode symbol, right? But when it comes to G0 diode, it is shown this way, representing the letter Z. Understood? So G0, here is the symbol Z. Any diode shown like that, try to realize that it is a G0 diode. Next. G0 diode is used as a voltage regulator. The main application of G0 diode, it acts as a voltage regulator or voltage stabilizer. Have you ever seen a stabilizer connected to a refrigerator, TV, etc.? These electronic components. So it stabilizes the voltage. It provides a constant voltage from a source of fluctuating voltage. G0 diode maintains stability in the output voltage because it is operated in the reverse bias mode. Understood? Next. After G0 diode, we have a photodiode. Photodiode is the diode. Photo means light here. So, a device or a diode which converts light energy into electrical energy is a photodiode. Symbolically, the photodiode is shown like this. As usual, there are two materials, P-type material. This is P side and this is N side of the material. And this is the depletion region. Above that, there is a window through which light can fall on this junction region. Okay, light falls on the junction region. It is fabricated with a transparent window. Transparent window. Here is the transparent window to allow light to fall on the PN junction of the diode. Through the transparent window, light falls on the PN junction of the diode. So, this falling light carries energy, where that energy is given by h nu, where nu is the frequency of radiation. That is the energy it absorbs and forms the hole and electron pairs. These hole and electron pairs will contribute to the conduction. Just like a Zener diode, even a photodiode is operated under reverse bias. Only LEDs, light emitting diodes, are operated in forward bias mode, and Zener diodes and photodiodes are operated in reverse bias mode. In competitive examinations, questions can come based on these points also. So try to remember this. Photodiode is also operated in reverse bias mode. When the photodiode is illuminated with the light contains photons, right? And these photons carry energy h nu. If then this energy is greater than the energy gap of the semiconductor, what is energy gap? That we have discussed in the first session, electronics 1. If you don't know, please go through that so that you will have complete clarity on these concepts. Okay. If the incoming energy is greater than the energy gap, that means E, incoming energy is greater than the energy gap, then electron hole pairs are generated near the depletion region, and due to these electron hole pairs, conduction happens. Okay, so that is photodiode. Now coming to the applications of photodiodes. Photodiodes are fast acting devices. They respond very quickly. Fast acting devices and can respond to signals in nanoseconds. What is nano? Nano meaning 10 power minus 9. Such a small value it is. Nanoseconds, 10 power minus 9 seconds time. Hence they are used in switching circuits to switch on and to switch off in switching circuits to quickly respond. These photodiodes are used. They're used for detection of visible and invisible radiation even. They respond to the visible light as well as invisible radiation. They're widely used in optical communication as light detectors. Light detectors. Optical communication. They're also used for the measurement of intensity of light and used in light meters, especially cameras and also scanners. These photodiodes find applications in cameras, scanners, light meters. Okay. They're used in security devices like fire alarm, burglar alarm, etc. These are the applications of photodiodes. Okay. Interesting, right? For more such interesting concepts and videos, you can subscribe to our channel, Time for IITJEE NEET. These videos will definitely enhance your subject knowledge, and with that you can score well in your board exams as well as competitive examinations. Now, let us see another type of diode, light emitting diode, simply known as LED. Nowadays, these are very famous LEDs being used in household lighting, street lights, vehicles, automobiles as headlights, tail lamps, here and there, everywhere, LEDs. So what are these light emitting diodes? What material is used in fabricating these light emitting diodes? Let us see now. And see, it is a forward biased PN junction. As I told you, LEDs are operated in forward bias mode, whereas Zener diode and photodiodes are operated in reverse bias mode. It is a forward bias PN junction diode used for converting electrical energy into light energy. Photodiode converts light energy into electrical energy, whereas LEDs will convert electrical energy into light energy. Okay, reverse process it is. Usually gallium arsenide, gallium phosphide, indium phosphide are the usual semiconducting materials used for making LEDs. These are the materials, semiconducting materials used in fabrication of the LEDs. Gallium arsenide is used for making infrared LEDs, IR LEDs, whereas gallium phosphide, gallium arsenide phosphide, GaAsP, gallium arsenide phosphide are used for visible LEDs. The symbol of light emitting diode is shown here. This is the symbol of the LED. When a PN junction is forward bias, the recombination of electrons and holes releases energy. Energy is released in the form of heat and light. Light emitting diode, it emits light. So this is how light is emitted. It is because of the recombination of holes and electrons near the junction. And that light contains photons. Like that, an LED works. That is the working principle of an LED. Okay. Now, see, if LEDs are emitting light, light contains waves. What is the wavelength of these radiation emitted or light emitted? The wavelength is given by Hc by Eg, where Eg is the energy gap. Hc, H is Planck's constant, C is the speed of light in vacuum, divided by energy gap of that particular diode. Hc by Eg, that is the wavelength emitted. LEDs are always used in forward bias. You need to make a note of this point and remember this. Why only forward bias? Why not reverse bias? Because in reverse bias, no recombination of holes and electrons will take place in reverse bias. If there is no recombination, no energy is released in the form of heat and light. That's why they are used in forward bias mode. LEDs are operated in forward bias mode. Okay. Coming to the VI characteristics of LED, it is very much similar to a normal silicon junction diode. The VI characteristics, voltage versus current, VI characteristics of LED. It is similar to the simple silicon junction diode, but the threshold voltages are much higher and slightly different for each color as shown. See what all colors are shown here: violet, blue, green, yellow, red, different colors. So threshold frequencies or threshold voltages vary with respect to their color as shown here. Okay. The reverse breakdown voltage of LEDs is very, very low, and particularly they are operated in forward bias mode. The semiconductors used for fabrication of visible LEDs must at least have a band gap or energy gap of 1.8 electron volt. For visible LEDs, the minimum energy gap required is 1.8 electron volt. Noted? Now, let's see what are the advantages of these LEDs over conventional incandescent lamps. Nowadays, all the incandescent lamps are replaced by LEDs. Why so? Excuse me. One reason is for sure it is because of their long life, sturdiness, and see, LEDs need very low operational voltage. Power consumption is very, very less for LEDs compared to conventional lamps. LEDs need very low operational voltage, and hence they consume very little power for their operation. That is the attracting factor here. LEDs respond very quickly and no warm-up time is required for their operation. Very quick response. Though it is not that important, first point is very much important. Power consumption is very, very less. The light produced by LEDs are nearly monochromatic. Monochromatic means single wavelength, single color. Okay. And with bandwidths in the range of 100 angstrom to 500 angstrom range, we'll get the output light from LEDs. And another important point that attracts the attention of the public here is LEDs have long life, very long life, and their ruggedness, low power consumption and long life. And these LEDs have fast on-off switching capability. Though you switch it on, switch off quickly, it won't get damaged almost. Okay. Now, friends, if you have any requirement for classroom coaching or even for our online courses, you can visit our website www.timeforeducation.com. All the details are available in this website. Or you can visit your nearest time center even in your city. Now let's have a look at some questions based on the discussion happened today. The questions appeared in recent past entrance examinations. Here is one such question. Consider the following statements: A, B, C, D, E. 5 statements are given. Consider the following statements. Then question follows. The junction area of a solar cell is made very narrow compared to a photodiode. The junction area of a solar cell is made very narrow compared to a photodiode. B is solar cells are not connected with any external bias. Solar cells, they are solar cells. They are not connected with any external bias. Yes. LED is made of lightly doped PN junction. Is it? Is LED made of lightly doped PN junction? No, it is heavily doped PN junction. To get more number of holes and electrons recombinations for effective emission of light, It is heavily doped, not lightly doped. So you can rule out this statement C. Increase of forward current results in continuous increase in LED light intensity. No, LED light intensity won't increase with increase in forward current. Okay, so D is not correct. LEDs have to be connected in forward bias for emission of light. Is it true or false? How are these LEDs operated? GNR diodes are operated in reverse bias, photodiodes are operated in reverse bias, but LEDs are operated in forward bias. Correct. Now let us see what are the options given. Based on that, we can make out the correct option. Choose the correct answer from the options given below. A, C, E only. C is anyway wrong. So you can rule out option A. Since C is wrong, you can rule out option C also because it says AC only. Now we are left with BE, BDE. BE, BDE. B and E are common. Coming to D, increase of forward current results in continuous increase in LED light intensity. That is not correct. So you can rule out option D. So what is the correct option now? It's only option B. B is the right answer for this question. Understood? Next. What is the current through the battery in the circuit shown below? Here is a circuit. A 5-volt cell is connected here. There are 2 diodes followed by 2 resistances, 20 ohm each. First, check how are these diodes? Are they in forward bias or reverse bias? Then you can measure the current through the battery. What is the current passing in this path? I. See, battery positive on this side, negative is on the other side. This battery positive is connected to the diode positive and battery negative is connected to the diode negative. Even for the second diode, it is the same scenario. P and N of the diodes are shown like this. Okay. We know that this side it is P and arrowhead indicates the negative side, P and N. Now clearly battery positive is connected to the P side of the diode and battery negative is connected to the N side of the diode. So both these diodes are in forward bias mode. Forward bias. So what is the speciality of forward bias? In forward bias mode, diode conducts. Right? It does not offer any resistance. So there is no resistance in this part. Then what is the resistance in the upper path? Only 20 ohm. Similarly, in the lower path, diode is not offering any resistance here, but there is an external resistance 20 ohm. How are these two resistors? Clearly, they are connected in parallel. What is the effective resistance then? R is R1, R2 by R1 plus R2 in parallel combination. That means 20 into 20 by 20 plus 20, 40. That comes out to be 10 ohm, right? 400 by 40, 10 ohm. Once you know resistance, applied EMF is given here, 5 volt. Then what is the current? I is E by R. E is 5 volt by resistance 10, which is 0.5 ampere. So 0.5 ampere is here in option D. Okay. Another question. A full wave rectifier circuit consists of 2 PN junction diodes, a center tapped transformer, a capacitor, and a load resistance. Which of these components removes the AC ripple from the rectified output? What is used out of these components which is used to eliminate or remove the AC ripple from the output? What is used? It's the capacitor, right? Do you remember? Already we have discussed it. See, here is the full wave rectifier. In this full wave rectifier, you have 2 diodes, a center tapped transformer, a capacitor, a load resistance. These are the components. Now to remove the AC ripple from the rectified output, what is used particularly? That is only a capacitor. The capacitor acts as AC filter So capacitor is used to remove this. That means B is the right answer for this question. Okay. Next. The increase in the width of the depletion region in a PN junction diode is due to increase in the width of the depletion region. Depletion region width may increase or decrease depending upon the type of bias. In forward bias, conduction takes place, width of the depletion region decreases. But increase in the width of the depletion region is just because of the reverse bias. So it's only due to reverse bias, not due to both forward and reverse bias. It's not due to increase in forward current. Only in reverse bias mode, width of the depletion region increases. So right option here is option A. Okay. And another one. Which of the following represents forward bias diode? See, diodes with a resistance are given here with the different voltages applied across positive P side and N side. Observe these values, which is in forward bias mode. Let us start with option A. Here for diode, this is P side and this is N side. On P side, you have -4 volt connected. On N side, -3 volt connected. Both are negative potentials, not positive and negative. Both are negative. But here you need to consider higher and lower values. Higher value and lower value. Of -4 and -3, which is higher? See, this is higher compared to -4. -3 is more than -4. Means higher potential is applied to the negative N side and a lower potential is applied on the P region. That means it is in reverse bias mode. It is reverse biased. Coming to the second one, option B, -2 +2. -2 is given to the P region and +2 is given to the N region. It is like positive terminal of the battery connected to the N region and negative terminal of the battery is connected to the P region. That means it is reverse biased. Isn't it? Now, C, 3 volt and 5 volt. We know very well that 5 is more than 3. That means higher value is connected on the N region, lower value is given to the P region. Same as the option A, it is also a reverse bias mode. Okay, what is your answer then? A is not correct answer, B is not correct answer, C is not correct answer. Obviously, it has to be D, right? Let us check with the given values even. See, here is 0 volt connected to the P region and -2 volt connected to the N region. Comparing between 0 and -2, 0 is higher. So higher value is given to the P region and lower value is given to the N region. It's like battery positive to P region, battery negative to the N region. So this diode is in forward bias mode. Which one of the following represents the forward bias? That is D. So D is the right answer for this question. Okay. So hope you have enjoyed this session, enjoyed solving these questions. I'd like to conclude this session here. Thank you very much for watching. See you in the next session. Thank you.